Back to another video by yours truly, Joshua LeClaire. In this video, we're going to go ahead and take a look at some more advanced displacement problems. And we'll go ahead and start us off with an example problem, and we'll kind of explain why this problem is a little bit more advanced. And I think it'll be pretty easy to see in comparison to the first video that you watched. Alright, so let's go ahead and take an example such as my room. So let's say you start at my room and your goal is to walk to Mr. Obenshain's office. Alright, so in order to do that, we're going to have to go down the corridor, take a right, and we're going to walk a ways down this longer corridor all the way to the B wing, and then we're going to hang a right and kind of imagine, so I'm not taking any diagonals here, so I'm really just kind of moving in straight lines. So I'm walking in a straight line down my hallway, I'm heading right, taking a right, I'm heading in a straight line down that hallway. Then when I do that, I'm going to have to take a little bit of a right turn again for a short distance to get into the administration hallway. That will also take me along part of the B wing. And I'll walk down that hall for a few paces and then hang another right into a small little connecting hallway, and then I will be in the longer hallway where I'll hang a left that will take me all the way to Mr. Obenshain's office, Mr. O's office. Alright, so at this point let's go ahead and get our values in here. So and before we do that, let's go ahead and set up a compass as well so we know our direction, because when we talk about displacement, we're going to talk about direction as well. So heading away from my room, you'd be going north, and Mr. Obenshain's office is a bit east of me. So we can kind of assume the direction of movement is going to be, according to our chart here, a little bit northeast from my room to his room. Alright, so the values that we walked, so the quantities that we walked, that magnitude. Let's say this is 25 feet, and we know this corridor is a little longer, so that's going to be 40 feet. And then let's say we walk about 15 feet this way, and another 6 feet into that little hallway along the B wing and admin areas. And then we are going to take a small little hallway to get into the carpeted areas, and then let's say about 20 feet from there to Mr. O's office. Alright, so boom, this is kind of the direction that we've traveled so far. Cool. Alright, so our total distance travel is pretty easy to figure out. We just got to add all those values together, and we get a total distance of about, and not even an about, although it is an estimate, a total distance of 110 feet. Okay, so that is the total distance traveled, but that, however, is not our displacement as we discussed before. Our displacement is going to be the straight line that exists between my room to Mr. O's room. So what if I could just walk through all of the walls and just walk in a perfectly straight line, which represents the shortest distance between my room and his room. Alright, now what we can see there is that we have a slight angle. Now this is just a hand-drawn graph, so it's not perfectly to scale. I don't have grid paper in front of me, although grid paper could help, because I could maybe imagine that every square represents 5 feet or so. Alright, so but I'll show you, you don't even need grid paper. You could just do this on line paper or just on blank paper. Alright, so here's the problem. In the previous problem that we looked at, that's a simple displacement problem, it was very easy to see where the right triangle was. On this one, it's not so easy to see what the right triangle is, and it's not very easy to know how long the sides of that right triangle are, so we can set up Pythagorean Theorem and then just plug everything in and solve for C like we did before in the other one. So what we're going to do is a little method in which we add and subtract values, so distance values, based on the direction of travel. And what we're going to use is a coordinate grid to do this. So if you imagine a coordinate plane, what you guys know is that everything that moves to the right is counted as a positive, everything that moves up is counted as a positive, anything to the left is negative, and anything down is negative. What we're going to do is assign those values to our chart. So if you look right here, you can see that we have 25 feet going up. I would say that would be a positive 25 feet then, all right? We also have 40 feet going to the right, and according to a coordinate plane, anything that's going to the right is also a positive. Then we move 15 feet down. Now, of course, we're not actually going down, but on our paper, it looks like we're walking down or south. And so that means that we are going to count that 15 as a negative, so negative 15 feet. Then we walk 6 feet to the right, which would be a positive 6 feet. And then we walk another 4 feet down, which is going to be a negative 4 feet because we're going down according to our Cartesian plane, or south. And then we walk 20 feet again to the right. And anything to the right, we're going to count as a positive. All right? Now, what we'll do is we'll take all of the values that go left to right, and we're just going to put them together. So add them up. So we have a positive 40 feet. Okay, and I'll cross that one off to show that I used it. Then we have a positive 6 feet. Cross that one off because I used it. Then we have a positive 20 feet. And we'll cross that one off. All right, now if I put all that together, what I can see is that, first of all, they're all positives, which means I just continued to move to the right and I never moved to the left. So I walked to the right a total of 66 feet. All right, now we'll come back to that 66 feet in a second. All right, so let's see, how about everything that is vertical? So how much vertical motion did I have according to my paper? So again, on my drawing. That doesn't mean I was walking vertically in real life, it just means on my drawing it looks vertical. Well, I have a positive 25 feet. And I have then a negative 15 feet because I walked down on my paper. Then I walked another 4 feet down, which is on a Cartesian plane going to count as a negative value. And what I can see here is I have a positive 25 feet that I moved away from my room, and then I moved back about 15 feet, and then back another 4 feet. And if I put that all together, positive 25 plus a negative 15 plus a negative 4 leaves me with 6 positive feet. And you can see that because a positive 25 minus a 15 is 10 feet, and 10 feet minus 4 feet is 6 feet. All right, so you're wondering, okay, well, how does this help me create a right triangle? Well, what I just solved here were the sides of my right triangle. On one side, I have a total of 66 feet that I walked left to right. On the other side, I have a positive 6 feet that I walked up and down on my piece of paper. So what I'm going to do is draw that onto my chart or my diagram. That's not going to work. There we go. And there it is. And the values are, I walked up and down a positive 6 feet from where I went, and then I walked a total of 66 feet to the right of where I started. So the 6 feet, since it's positive, is saying that I walked up positive 6 feet from where I started. The positive 66 feet means that I walked to the right, which on a Cartesian plane is positive 66 feet. Now from there, it's pretty easy, because there we can see that it's a right triangle, and I'm going to label the sides A and B, and then plug it into my Pythagorean theorem. And I'll work through this a little bit more quickly because it's really just plugging things in and solving for those values, so squaring each one of those. And I'm going to pause here because what you should see is that I end up with a really big value for a squared. I end up with a really small comparative value for b squared. And when I put them together, I get a value that's pretty close to what a squared was. So a was 66 feet, and I know that a squared is 4,356. Well, this number is pretty close to 4,356. So I know that c squared is going to be, or c is going to be very close to 66. And if I find the square root of each of those sides using my calculator, then I can see that it comes out to be about 66.3 feet. And that's because this value, or this b value, this b squared value, it just didn't matter that much. It's not a big number compared to this value right here. And so I ended up with a total value for the hypotenuse that's basically what a was, a little bit higher. So I just solved that my displacement is going to be 66.3 feet. Now, in order for it to be truly displacement, we need to also put a direction on there as well. So I'm going to move the hypotenuse, and what you can see is that my hypotenuse is just going slightly above east. So I don't know that I would actually call that northeast. I would almost call that northeast-east, because it's kind of between northeast and east, but it's kind of closer to east. So maybe I'll call it northeast-east, but then that doesn't sound right. So I looked it up on the internet, and I found out that the true way of calling this, or the true way that you identify this direction, is by calling it east, northeast. So it's more east, but it's also a little northeast of east. Now, I'm not going to be a huge stickler on that, so as long as you identify that it's kind of east or kind of northeast, something like that, then that's a pretty good direction. But this is a way to be a little bit more accurate. So it's close to east and kind of northeast. All right, and I'll put my hypotenuse back, and that's the end of our video. And this represents a more advanced displacement problem in which it's not very clear where our right triangle is going to show up.